Today, we're diving into a problem that sounds simple, arranging numbers in a grid, but connects AI, optimization, and real-world impact in ways you won't expect. We're talking about balanced Latin rectangles. And here's the twist. We're letting AI teach itself how to solve them faster. What are Latin rectangles? First, the basics. A Latin rectangle is a k by n grid, where k is less than or equal to n. Each cell contains a symbol from 1 to n, and here's the rule. No symbol repeats in any row or column. Think Sudoku, but rectangular. Now here's where it gets interesting. In experimental design, agriculture, psychology, drug testing, you don't just want any Latin rectangle, you want a balanced one. Why? Spatial correlation. If all your treatments cluster together, environmental factors contaminate your results. Balance means the distance between any two symbols across all rows should be as equal as possible. We measure this with imbalance, the sum of how far each pair deviates from the ideal distance. For this 3 by 4 rectangle, the imbalance is 4.0. Just lower is better. Here is a simple example to help you understand the issues at stake. Imagine a field full of seeds whose growth capacity we want to observe. Let's take this example with the sun shining mainly on the seeds in the upper left, and a water source mainly feeding the seeds in the lower right. If we take a field with poorly distributed seeds, it is easy to imagine that some seeds will grow better because the tests are poorly distributed. Latin's squares guarantee good distribution. We can therefore understand how crucial it is for each pair of varieties to always be at the same average distance across all rows. This is a simple example, but Latin's squares can be used in many fields, such as medicine and drug testing, for example. So why can't we just solve this? Combinatorial explosion. For a 12 by 13 rectangle, you're searching through a space so large it makes the number of atoms in the universe look tiny. Traditional solvers, constraint programming, mixed integer programming, slow down and basically stop working on larger cases. For decades, researchers have known the best imbalance values for many configurations, but improvements? Rare. Until now. The secret weapon? Streamlining constraints. These are extra rules you add to your model that cut away unpromising parts of the search space. They're not required to preserve all solutions. They can even eliminate the optimal one. But when they work, they guide the solver toward high-quality solutions fast. 3 main types: symmetry-breaking constraints that eliminate redundant solutions, implied constraints that help the solver propagate information, and dominance-breaking constraints that cut suboptimal regions. The problem? Designing these has always been manual, tedious, and required deep expertise. What if we could automate it and find original ones? Enter large language models. Here's the brilliant idea. Feed the problem's mini-zinc model, that's the constraint programming language, into GPT-4, Claude, Gemini, or DeepSeek, and ask it to generate streamlining constraints. The LLM analyzes the structure and proposes creative rules. About 14% have syntax errors and get discarded. The rest? Pure gold. The system tests each streamliner for a few minutes, keeps the winners, and iterates. It's like having an AI intern that generates hundreds of optimization ideas while you sleep. They use 3 prompt strategies. Basic prompts asking for 5 creative constraints, combination prompts requesting multiple constraints that work together, and detailed prompts including full problem descriptions. The diversity matters. Different LLMs find different patterns. The paper introduces 2 orchestration strategies. Strategy 1. Incremental warm start. Start with a 1-minute baseline solution. Generate 5 streamliners, test them in parallel, and if any finds a better solution, that becomes your new starting point. Your warm start. No improvement after 5 iterations? Increase the testing time by 2 minutes. This exploits a key insight. Optimization problems find their biggest improvements early. Strategy 2. Evolutionary framework. Build a population of effective streamliners. Sample the top performers, weighted by their inverse imbalance to the power of -4, favoring the best, and ask the LLM to combine and mutate them into new variants. Its genetic algorithms meets generative AI. The diversity is stunning. Almost no streamliner appears in the top 3 for more than 2 instances. The results? Record-breaking. They improved 32 out of 44 instances compared to the best-known bounds, some established over a decade ago by constraint programming experts. For example, the 12 by 13 instance dropped from 352 to 274, a 22% improvement. The 11 by 13 instance went from 278.6 to 224, a 20% reduction. These aren't just numbers. They're better experimental designs for real-world applications. And here's the kicker. Some streamliners found in just 3 minutes outperformed running the original model for 4 hours. The LLM even rediscovered known symmetry-breaking constraints and invented entirely new ones, like mirror symmetry constraints that enforce horizontally symmetric values summing to n+1. So, why does this matter beyond rectangles? This is a proof of concept for neurosymbolic AI, combining neural networks' pattern recognition with symbolic reasoning's precision. The LLMs don't just generate random constraints. They understand the problem structure enough to propose meaningful pruning strategies. And crucially, every suggestion is verified. The solver tests them, so hallucinations don't matter. This approach could generalize to scheduling, resource allocation, network design, any combinatorial optimization problem where human expertise is the bottleneck, the limitation. No optimality proofs. These methods find better solutions faster, but can't prove they're the best possible. For many real-world applications, that trade-off is worth it. The vision? Constraint solvers with built-in LLM copilots, automatically generating streamliners as they search. The future of optimization might not be better algorithms alone. It's better algorithms plus AI that learns to guide them. From rectangles to real-world impact, this is AI making AI solvers smarter. Thanks for watching, and I hope that the explanations were clear enough. This video was based entirely on the research paper Balancing Latin Rectangles with LLM-Generated Streamliners.